Hi, this is Ivan. Today we're going to be talking about this exercise from Durrett's probability textbook. This exercise is about weak convergence and convergence in probability. So let's get started. First, we know that this sequence of random variables xn goes to x in probability. We want to prove that xn converges to x weakly. Let's copy this problem here first. This is the first part of this problem. Let's use different colors to highlight them. All right, now let's invoke a theorem from Durrett's textbook. It's called theorem 3.2. I happen to have this theorem here. It says xn goes to x in probability if and only if for every subsequence there exists a further subsequence that converges almost surely to the same limit. So let's copy this conclusion here. For any subsequence in sub k, there exists a further subsequence. Let's call this further subsequence in KL. So with x in KL convergent to x almost surely, of course, as in this case, L goes to infinity, right? So this is what we can get from the conclusion, from the condition, the purple part. Now to proceed, let's invoke a different theorem called theorem 3.2.9. It says this weak convergence is the same as the following statement: for every bounded continuous function, we have their expectations converge like so. So it has a famous corollary. Let's call this corollary 3.2.9 prime. It's derivative. So it says, if we know xn goes to x almost surely, then we can deduce that the same sequence of random variables xn goes to the same limit x in distribution, meaning weakly. This is actually a direct consequence of this theorem. There's nothing mysterious here. So the proof is by, of course, this theorem, and also by bounded convergence. Notice this symbol was invented by me. It means bounded. And the second symbol was introduced by my professor, Professor Ken Alexander, my probability professor. It means convergence. So there's an arrow and a C in between, like this. So now let's apply this corollary here. We can get by this corollary 3.2.9 that this sequence x in k L goes to x weakly, because that's actually what the sequence directly tells us. We know, almost sure convergence can directly imply weak convergence. That's it. And by one of our previous exercises, exercise 2.3.6, we know that there exists a metric, which is the Levy metric, for convergence in distribution. Is everything okay so far? This is one of the exercises we did last time. And I should mention that almost sure convergence does not come from any metric or even from a topology. So almost sure convergence is an unlucky convergence. But fortunately, weak convergence corresponds to a metric. Therefore, it allows us to apply a new theorem called theorem 2.3.3. I happen to also have one here. This is a famous general theorem about topological spaces. It says if every subsequence has a further subsequence that converges to the same limit, then we can directly deduce that the entire sequence converges to this limit. Notice here, this is the Levy metric. Corresponding to the Levy metric, this convergence means weak convergence. So in the Levy metric. So now by this theorem, we can directly get our final conclusion. Xn goes to X, which is what we wanted to prove. So that's it. Any questions here? All right, so next let's look at the second part. Usually when we prove that a theorem or a statement is true, then naturally we would want to ask whether its converse is true or not. But unfortunately, in this case, the converse is not true in general. But fortunately, when this limit X is a constant C, then the converse is indeed true. Speaking of the constant C, this semester I'm a TA for Calc 1, and we deal with a lot of constants in integration. So when we learn indefinite integrals, a lot of my students tend to forget to add the constant C to the final antiderivative result. So I told them that if you forget to add the constant C, then the instructor will give you a C. This is kind of fun. So again, let's copy this problem here. Now we know that Xn goes to C weakly. We want to prove Xn goes to C in probability. So by definition, a sequence going to C in probability means for any epsilon greater than 0, the probability of this event Xn goes minus C greater than epsilon goes to 0, of course, as n goes to infinity. Likewise, the definition of the condition says the distribution function Xn goes to F, where in this case, F is the distribution function of this constant C. By definition, that means capital F equals 1 if X is greater or than or equal to C, and 0 if X is less than C. So this is the distribution function of C, and Fn are distribution functions of this sequence of random variables. Again, by definition, the weak convergence for distribution functions just means Fn y goes to f of y for any y that are continuity points of capital F in this case. So that's it. Let's again use different colors to highlight them. So this is the condition known here. This is what we want to prove. So let's prove this. For any epsilon greater than 0, we have this probability. Let's copy this expression directly. We want to prove this probability goes to 0 as n goes to infinity. So it equals, of course, when 1 minus p Xn minus C less than or equal to epsilon, because of course this event is the complement of this event. So the sum of their probabilities is 1. And notice this event is the same as C minus epsilon less than or equal to this event xn, and less than or equal to 1 c plus epsilon. This is what the absolute value means here. Therefore, this entire difference is less than or equal to 1 minus p of c minus epsilon xn c plus epsilon. And this, let's see, this probability by definition is the same as the distribution function fn of c plus epsilon minus fn c minus epsilon. Therefore, let's copy this, what we have deduced here, 1 minus fn c plus epsilon minus fn c minus epsilon. Is that clear? And now let's make use of our condition here, or its equivalent statement by definition. So we know that fn goes to f for any continuity points of capital F. So this can, together with c plus or minus epsilon, are in C of F in this set. This set is the continuity, is the set consisting of all continuity points of this capital F function. Therefore, we have Fn of C plus or minus epsilon goes to Fc plus or minus epsilon. Is that clear? Because, for any y, we have this statement, then in particular, when y equals this point, these 2 points, then it's still true. So that's it. All right, so next, we can now deduce that this difference goes to 1 minus f of c plus epsilon minus f of c minus epsilon by this conclusion here. Is that clear? Because, Fn c plus epsilon goes to f of c plus epsilon by this, and this one likewise goes to capital F of c plus epsilon. So that's it. And then next, let's continue this probability. It equals now, let's see, by the definition of capital F, like so. Whoops, here. We have, so by this orange part, we have this difference is actually equal to 1 minus 0. Again, by definition, because of course, c plus epsilon is greater than c. Therefore, the result is just 1. And likewise, this is 0. So that's it. So we have the result, final result is 0. Of course, as n goes to infinity here. So that is what we want to show, because, by this definition, by definition, we do have xn goes to x in probability. So we're done. This is the definition here. All right, any questions? Great, thanks.